Okay, continuing on with week 3. I believe this will be video 4. And in the previous video, we did the underdamped constants using initial conditions. So here are the critically damped constants. We won't spend as much time on these as we did on the underdamped because underdamped is a more frequent result. So there was 3 different cases that we found when we had used the damped equation of motion, and we found the solutions. There's 3 possible solutions before we had underdamped. Here's going to be the critically damped, right? And here's the form of this. And we got this because we had 2 roots of the characteristic equation, I guess we'd call it that, where there were 2 equal roots that were 2 equal in real roots. And so here is the type of solution that we have for that. And I believe this should be omega d times time. So if the time equals 0, so this is as a function of time, we're going to have this initial displacement, which is going to be c1 plus c2 times 0 e to the 0, right? So that just goes to 1. That just goes away. So c1 is equal to the initial right there. There's my therefore. If we take the derivative of this equation right here, the ddt of that thing, we get x dot t is equal to negative omega n. So I'll take the derivative of this part first and bring it to the outside. c1 plus c2, and I probably should go ahead and put the x naught in there, right? In case it applies, x naught. C2, but that's going to be times, well, I want to keep it general. Okay, t times e to the negative omega dt, right? So that was just first doing this part first, and now we're going to add to it the derivative of the first part, and so the c1 goes away, and we're going to end up with c2. Okay, the t goes away because we took the derivative of it, and so all we're left with is e to the negative omega dt. All right, so now say at t equals 0, right? So that's the velocity of this, and so we'll go x dot of 0. It's going to be that initial velocity is going to be equal to negative omega n x naught plus ct times 0 times e to the 0 plus c2 e to the 0. And summing all that up, we'll get x dot naught is equal to negative omega n x naught plus c2. Therefore, c2 is equal to x naught plus x times omega n. All right, so now we have the complete solution, and that's x naught plus x naught dot plus x naught omega n should be times t, right? Yeah, t raised, and then e raised to omega n. Ooh, I said n right in here. Ooh, I have to decide. I think I made a mistake up at the top. It should be n. My bad. And I probably made it all the way along. Well, see, I got it right there. All right, so this should be n, Did I make any accidental D's? No. So it's going to be NT. So I believe this is the equation. If you had initial conditions, you know the initial conditions. This would be what the position would be with respect to time. It's important to note that this is not a reciprocating thing, right? This doesn't have a bouncy to it. It kind of like it dies out. And as I mentioned in video 2, maybe that behavior is similar to what you could expect from having a door. Well, probably more the overdamped than this one. This is just it has to be the perfect combination of parameters for this behavior to happen. It has to have just the right amount of damping compared to the mass and the stiffness. But for an overdamped door, you would like start to, here's the wall, and here's like maybe a hinge, and here's the door, right? And so you can swing it really hard, but it'll slowly close. Of course, by the way, this is a math model, and it actually will never actually 100% reach 1 or end to the thing. So you know that actually the door will eventually close. So we do go to the other version of this for completeness. This is the overdamped. All right, so it doesn't really result in too much of a difference when it comes to the graphing of the thing. If you were to look at a graph, there's a slight variation. But here is the what you get if you have overdamped. Now these are two real but different roots, and we don't bother with putting in what the lambda 1 and the lambda 2 are going to be. Those are values that we could find. If you recall from the previous videos, that we would get the roots of the characteristic equation, which looks like this right here. So if you find these two roots, the roots of lambda 1 and lambda 2, two real but different values, that's what you would get for the lambdas. So the initial conditions at time is equal to 0, we'd find that x, which is x dot, is going to be C1 times e to the 0 plus C2, which is e to the 0, right? So therefore, x naught is equal to C1 plus C2, right? So you don't quite know yet what they are, but we do know that when you combine those two together, they end up with the initial position. Now, if you take the velocity of these things, what you end up getting is lambda 1 C1 e to the lambda 1 t plus lambda 2 c2 e to the lambda 2 t. So at t equals 0, and x dot naught is going to be equal to lambda 1 c1 e to the 0 plus lambda 2 c to the c2 e to the 0, and therefore x naught dot is equal to lambda 1 c1 plus lambda 2 c2. All right, so we have two equations and two unknowns right here. This equation and this equation, and presumably x naught is known and x naught dot is known, and we do know the lambda 1 and lambda 2, so we can solve these things, and we could write out I guess the way I did it is I took c1, I set it equal to x naught minus c2, and I substituted into, so if I call this equation 1 and equation 2, I substitute into 2, so that I find that I have x naught dot is going to be lambda 1 times x naught minus c2 plus lambda 2 c2. So c2 is therefore going to be x dot naught minus lambda 1 x naught divided by lambda 2 minus lambda 1. Similarly, c1 is equal to x naught minus all the stuff we just wrote. Because I could put this back into 1. I could put c2 back into 1. And I am missing, there you go, that guy, I think that's right. And you go lambda 2 minus lambda 1. And I'm sure there is some rearranging that can be done, but we can just go ahead and write out this equation if we needed to. If there was some like big motivation to figure out what this motion was going to look like. And although it might be tedious to do, we would be able to learn something from it, so it would be worth it. But very similar to what I just wrote out in the previous page when it came to the critically damped problems. What you would find in the behavior here. All right, so here's the equation that would represent that. What we would find is something to the essence of you might go bloop, boom, and it might be like a steeper descent than this one, right? So it might have a quicker drop off. But anyway, so that's just really this video right here is really for completeness. I don't know how often you would actually need to know the critically damped equation, but it doesn't make sense not to be thorough, so I'm being thorough. Next video.